So my name is Rob, and I'm a particle physicist, or a particle cosmologist more specifically. I work and teach at Royal Holloway, University of London, and I live here in Southend, and I give quite a few lectures at the museum kind of throughout the year. So some of you I know I've seen before, which is lovely to see you again, and more of you I hope to see again next time if I haven't bored you to tears by the end of this. So we're scheduled for an hour and a half, but I appreciate an hour and a half is probably more than 99.9% of the population can stand to hear about particle physics. So if anybody needs to leave at any point, I won't be at all offended, just sneak out front, it's absolutely no problem. And at 1 hour, I will sort of give a, right, we've had an hour, now I almost encourage you to leave, or you're going to be, you must be completely weird if you're still here after an hour, although I hope you are. And I want to leave a lot of that time for questions, although if questions come up as I'm talking, just shout them out, stick your hand up, and we'll talk about them then and there. I don't want this to be too formal. So the title of our lecture today is Building a Universe from Scratch. Now, I should give a disclaimer. I'm unfortunately not going to teach you how to build your own universe. It might be slightly misleading. What I'm going to do more so is talk about the basic ingredients and the basic laws of nature that allow our universe to take the shape it does today, and how we understand that at a kind of subatomic level. That's the goal. I want us to leave today with an idea of how the physics of the subatomic works, what the rules of the game are, what the different pieces are, how they fit together. That's my goal, okay? And also, perhaps more importantly, what the mysteries are. What are the things we still don't know? Because there's a huge amount we still don't know about particle physics and the subatomic world. So I particularly want to emphasize the things we don't understand. And there are some young future scientists in the audience here today I can see. So these are challenges to you. These are not abstract questions for someone else to solve. These are things I want you guys to solve in the future, okay? So there's a QR code here, which you can scan if you like. All it has are a couple of links down here to some previous lectures I've done and an interesting podcast about dark matter by a guy I used to work with. It also has a sign-up link to a regular science drop-in I run at the museum, which is every other Sunday. I'll show you this link again later if you need it, but just in case you want to get it now to look at some of these links after, you can scan it, but if not, I will show it up again later, okay? So I'm going to move on from it now. Don't worry, it will reappear. So here's a rough outline of what we're going to talk about. We're going to start by talking about science perhaps in a more personal sense. I think it's quite common to maybe think about science in a very abstract way, but I really want to talk about what it means to me personally and what it means perhaps more philosophically to humanity as well. Then we're going to get on with the bulk of the lecture, where I'm going to talk a little bit about matter and energy. We're going to pick matter apart into what we think are its most fundamental constituent pieces, and we're going to try and learn about how these pieces fit together along the way. We're then going to talk about the rules of the game. So what are the rules of physics that govern the subatomic world and this bizarre science we call quantum mechanics or quantum physics? And I say science because it is a science. I think sometimes quantum mechanics, it gets a bit of a, almost weird, wooey kind of vibe around it, but actually it is a science. It makes measurable predictions we can test. That is perhaps the most bizarre thing about quantum mechanics, is that it is real, it is science. It is not just complete gobbledygook. We're then going to talk about two of the kind of most important open problems in particle physics that we still don't yet know how to resolve. So one of these is the existence of dark matter, the fact we know it's there, but we've got really no idea what it actually is. And this idea of quantum gravity, the fact that gravity does not quite behave in the same way as the other forces of nature. We'll talk more about that later. But first of all, I hope you'll kind of indulge me on a bit of a sort of personal reflection for a few minutes about why we care about any of this. Why does anyone care about doing science and answering these questions about the subatomic world? It's an important question. The sort of practical evidence of why we care about science is self-evident. You hold the fruits of those labors in your hand in your smartphone. You ride in them on your way to work in your car. Your home is filled with electricity and water and gas that could not be possible without the endeavors of generations of scientists. But if you ask any scientist why we do science, they will not mention any of those things, because that's not why we do it. So I've kind of broken down what science means to me into 4 pieces. So the first piece is collaboration. Ultimately, science is a team sport, and that's not just because modern science is difficult enough that you couldn't do it in solitude. It's because in these collaborations, and dare I say friendships, we renew our passion and we renew our motivation to learn more about the world and uncover the way nature works. Isaac Newton has a great line where he says, he writes, "If I have seen further, it is only by standing on the shoulders of giants," which is a great line, but I think it misses something crucial. What Newton misses are the many other people stood on those same shoulders, not above or below, but on the same level, side by side and arm in arm. Not a hierarchy, but a level playing field of people trying to learn more about the universe. The other thing science means to me is mentorship. It means learning from others, learning from your teachers, from your colleagues and from your students, perhaps especially from your students. They are who I feel I learn most from. It means passing on that knowledge in your turn. Every single scientist that has ever lived has benefited from the kindness and munificence of their predecessors. And that mentorship is not done for any hope of reward or any hope of reward greater than the passing of that stewardship of this great and ancient tradition down the generations, holding hand from one generation to the next for hundreds or perhaps arguably thousands of years of human history. It means discovery, which for me as a theoretical physicist involves a lot of very messy looking chalkboards, although I did once dabble as an experimentalist. I worked for a little while in a plasma physics lab in California. But this is really why we do science. It's the discovery. It's not for want of reward or recognition. It's because it's there. That's why we want to learn more about the universe. It's something that's in our DNA. And in all of our DNA, everyone in this room has that within them, that yearning to learn more about the universe and understand the cosmos from which we came. It's unavoidable. There's a feeling where when you discover something, you may be the one person on the planet that knows the thing you know or has observed the thing you have observed. And the only feeling better than that is when you share that observation, when you share that knowledge you've gained. It's like holding some kind of rare and tropical, beautiful bird in your hands. You can admire its colour and its softness and how wonderful it is. But the real joy is in letting it go, letting it spread its wings and fly out into the world. And lastly, science gives perspective. We are something like one of 10 million billion planets in the observable universe, as far as we know. And our Earth, as far as we know, is unique. It contains within it matter that has become sentient and is studying that same matter from which it sprang, our sort of cosmic mother that birthed us. And that is quite a remarkable thing, matter studying matter. And, our beautiful ocean world is remarkable in itself. It is placed at just the right distance from the sun that it can support liquid water. It has Jupiter in the outer solar system diverting cataclysmic asteroids that would otherwise destroy life on the Earth. It benefits from the benign influence of our moon, which tempers our seasons and makes life possible on our planet. It has a rich and vibrant ecosystem that is varied and magnificent, yet so vulnerable to our own short-sightedness as a species. That is the perspective science gives me. That's what it means to me personally. It might mean something totally different to everybody else, but I wanted to give that little reflection just so you kind of hopefully appreciate that science, it's not just a set of facts and figures, it's an ongoing process, it's a dialogue with nature, and it's something that brings not only information about the world and how the world works, but it brings a sort of spiritual fulfillment as well, which I think is not often emphasized. So that's my spiel anyway about what science means to me. Now I want to get on with the lecture proper and talk about particle physics, which is my research area. So we're going to start by taking a look at matter and energy and trying to break down particularly matter into its most fundamental pieces and study how these pieces fit together. So first of all, what is matter? And there's this great quote that technically is from George Berkeley, but I prefer to think of it from Homer Simpson, who quotes it in an episode. What is mind? No matter. What is matter? Never mind, which is great stuff. Basically, matter is stuff. You kind of know it when you see it, right? It ticks the boxes of solids, liquids, and gases, and also the more exotic things that don't fit into any of those categories. But it's something that if you held it in your hand, it would have a weight to it, okay? It's stuff. For example, and this is a non-exhaustive list, it includes rocks and frogs and soup. Some other examples do exist. Energy. Energy I'm going to describe as a property that makes matter do something. So perhaps it makes matter move, perhaps it makes matter change its form. You know, if you melt an ice cube, that is thermal energy causing a change to the structure of the ice cube. It makes matter do something. Energy, interestingly, can also be potential, meaning it doesn't yet have to be affecting matter in any way, but it has the potential to do so at a later time. You know, if you have a book on the top of your bookcase, it has in that state of being raised off the ground a kind of potential energy, what we'd call a gravitational potential energy, where if you give it a little knock and it falls down to the floor, suddenly all of that potential energy converts into motion. It converts into kinetic energy. So energy, something that makes matter do something or has the potential to make matter do something. So as a particle physicist, the job we have, our kind of mantra, if you like, can be summarized, I would say, in the following way. We want to discover the basic building blocks of all the matter in the universe and to understand the way these blocks fit together. So it's basically a glorified game of Lego. We're trying to figure out what are the pieces and what are the rules that govern how these pieces fit together, which sounds easy, but it turns out to be rather complicated. So I want to focus on this line here, basic building blocks. What do we actually mean by basic building blocks? So let's take this trio of particle physicists, and we're all made out of matter. Despite appearances, we are normal matter. And what we're going to do is we're going to zoom in. So don't worry, I'm not going to zoom in on my face massively. I'm going to zoom in on, so far, you're looking at an animal cell. So we've gone from a sort of human scale of about 1 meter to a sort of cellular scale of around about 100 micrometers is the rough size of a human cell. So cells are this basic unit of biological life that exists in pretty much all biological matter. And you know, they have their own functions, and we contain something like 100 trillion, I think, 100 trillion cells. You know, we in ourselves are this enormous, incredible ecosystem of trillions of other forms of life undergoing different processes, coming to the whole that is ourselves. So that's a human cell, about 100 micrometers across. But we can zoom in further. If we zoom in even further, the next level of precision down is something like a molecule. So these molecules here are collections of different atoms joined together in sort of particular combinations and mixes that lead to all the different chemicals we see around us. So H2O, shout out, who knows what this one is? Water, yep. CO2, what else would we call that? Carbon dioxide. Now this one's a hard one. C6H12O6, does anyone know? Who said glucose? Glucose, yeah, very good. Okay, so glucose, this is a kind of sugar molecule. Okay, and of course molecules can be much more complicated than this. Some of them can contain hundreds or thousands of molecules, of different atoms rather. But I want to zoom in even more. So now I zoom in and we reach the atomic scale. So we've now zoomed in to about 0.1 of a nanometer. So to put that a little bit into perspective, 1 nanometer is a billionth of a meter. So we've zoomed in 10 billion times on a person to reach this scale of an atom. And the atom has various components. It has a nucleus, this very large central mass, and then spinning around it we have electrons, these negatively charged particles that orbit the central nucleus. So is that it? Have we done enough zooming? I mean, if you ask the ancient Greeks, the name atom literally means indivisible. So the Greek atomists were philosophers that sort of did this experiment where they imagined if you were cutting a piece of cheese and you cut it in half and you cut it in half and you cut it in half and you keep going and you keep going, eventually you reach some fundamental indivisible unit of cheese. Okay? Now, we know there's no cheese particle, but there's something equivalent to that, right? There's an indivisible unit of matter. But it isn't the atom. The atom is quite poorly named in that respect. We can zoom in further. We can zoom in on the nucleus, and we find the nucleus is made up of two smaller pieces. So a particle called a proton and a particle called a neutron. Neutron is neutral, proton is positive. So physicists do sometimes make sense in the names we give to things, but this is what we have. These make up the nucleus, and now we've zoomed into a scale of a femtometer. So it's getting more and more obscure, the units of measurements we're using, but a femtometer is 1/millionth of a billionth of a meter. So, you know, where we were previously with the atom, we've now zoomed in 10,000 times. So the nucleus, you know, these particles that are in the nucleus of the atom are still inconceivably smaller than the atom itself. So is that it? Have we reached the end? Hands up if you think yes. No, we haven't quite reached the end. So we're going to zoom in again. We're going to zoom in on the proton. And we find the proton itself is made up of yet smaller pieces. So these yet smaller pieces we call quarks. And the proton is made up of two kinds. It's made up of two up quarks and two down quarks, which is physicists being a bit stupid with our naming. But this length scale, now this is an obscure unit. I actually had to look this up because I didn't know the name of it. This is 0.1 attometers. And an attometer is a billionth of a meter. So what that means, if you think about it in perspective, if you want to, you know, say go to a centimeter, you take a meter ruler, you cut it into 100 pieces and you've got a centimeter. You want to go from a centimeter to a millimeter. You cut that centimeter into 10 pieces and you get a millimeter. So that's sort of cutting in 100 and then cutting in 10. That's your millimeter. Now, just a micrometer means you take your millimeter, you cut it into 10 again, you cut it into 10 again, and then you cut that into 10 again, and that gives you a micrometer. Now that's only a millionth of a meter. If you want to do a billionth of a meter, you have to cut this thing into 10 18 times. Cut it into tens, cut it into tens, cut it into tens, and do that 18 times. So it's inconceivably small. There are analogies I can give you that will try and make this make more sense, but ultimately they don't make any sense either. This is an unconceivably small length scale to what we are used to. It's completely bizarre. So, what is the next question I'm going to ask, do you think? What do we think? What am I going to ask next? Can I go any further? Right, well, let's see. If we zoom in on this quark, oh, okay, we reach a bit of a roadblock. Now, what's smaller than a quark? The answer is we don't know. As far as we know, a quark is what we call a fundamental particle, meaning it just is. It's just made up of what it's made up of. It can't be broken down into smaller and smaller pieces. So if you go back to our kind of Lego analogy, these are like the tiny little one-by-one Lego blocks. Okay, you can build bigger things out of them. You can build protons out of them. You can build atoms. You can build molecules. You can build cells and people by stacking enough of them together. But you can't cut that one-by-one Lego block in half. It is what it is. There's nothing smaller than it. As far as we know, it could be that it has smaller constituent parts, but we've not yet seen any evidence of that. Now, you might be thinking, well, obviously it's got to be made of something. Everything is made of something. But at what point do you stop? At what point do you reach some fundamental level of matter that cannot be divided anymore? You know, it's an interesting question. Do we expect there to be more? Do we expect there to be smaller and smaller pieces? Or do we expect to reach some limit of indivisibility as the ancient Greeks predicted? What do you all think? Just out of interest, let's take a poll. Put your hand up if you think there must be something smaller. Okay, interesting. Put your hand up if you think that's probably it. Okay, so we're very much thinking there must be something smaller. There may well be. We just haven't discovered it yet. But then the question I guess I would ask is there always going to be something smaller? Are we always going to have a smaller and smaller and smaller piece? Is it just like, you know, it's turtles all the way down, we go on forever and ever and ever, or do we reach a limit? It's an interesting question, and it's not one we can really answer. So, as far as we know, the quark is fundamental. So, this is really what we mean when I mentioned earlier, we're looking for the basic building blocks. We're looking for these fundamental pieces of matter that cannot be broken up into any smaller bits, and to understand how they work. So, what other things just are? Well, the best theory we have of what matter is and how matter interacts, is in what's called the Standard Model of Elementary Particles. Arguably, this is possibly the best theory in the whole of science in terms of experimental precision. The predictions that this model has made and that we have tested have been tested to about 1 part in a trillion. So, that's like you're trying to measure your height and you measure your height to the 12th decimal place. It's an insane level of precision that no other theory in science can beat. So there's a lot of evidence, there's a lot of good things going for this model here. Now, you might be looking at this thinking, well, okay, great, good for you, physicists. You've got your own periodic table. It's got all the different kinds of stuff that you have. The chemists have their lovely thing here, which, although is a great piece of science, it's very limited. It only accounts for 3% of all the stuff in the universe, which is not much. So we've got our own one. It's got all the different kinds of matter, and it's got some other weird things over here. But I would say it's far more than that. It's not just a list. It's not just a table of stuff. It's a deep theory of how these particles interact, built on symmetries and laws of nature that are complicated and wonderful and very, very strange as well, like this bizarre science of quantum mechanics we'll come to later. But first of all, let's pick apart what some of these things are in the Standard Model. So first of all, we have this row here that has the rather technical name, the gauge bosons. Boson is just a stupid name physicists came up with. Gauge means something mathematical. But these are the particles that communicate forces of nature. So there are 4 forces of nature that are so-called fundamental forces. So fundamental particles, fundamental forces. You're seeing the pattern here. There is electromagnetism, the force that's responsible for electricity and the way magnets work. There are 2 nuclear forces, one that binds the nucleus together, one that's responsible for kinds of radioactive decay, and the last force I haven't mentioned, which we wish we could get away with not mentioning. What have I not mentioned? Gravity, right. 4th force is gravity. So the gluon, I'll tell you why we've named it the gluon in a moment. This is responsible for the strong nuclear force, which holds the nucleus together, or glues the nucleus together. So you can't say we're not imaginative. Now, the way this works essentially is if you have 2 sort of nuclear particles next to each other, they kind of fire a gluon at each other, and that firing of the gluon communicates the information that, hey, we should be sticking together. That's the way particle physicists model forces, via these exchange particles, these force-carrying particles. So the gluon is responsible for the strong force. The electromagnetic force is mediated by the photon. Now, this is the same particle that gives us light. That means we can see things in this room. The photons we see and the photons that mediate this force are the same particle, but they have a few subtle differences as well, but they are ultimately the same particle. So this is responsible for all electric and magnetic phenomena. And lastly, these Z and W bosons. They don't have as nice names, I have to say, but these mediate what is called the weak nuclear force, which is responsible for various kinds of particle decay, where one particle turns into another kind of particle. And I asked the question, what is missing? We mentioned there are 4 fundamental forces. 1, 2, 3. Something is missing here. We've got no description of gravity. Now, I'll come on later to talk about why this is a big problem and why we've not yet managed to solve it. On the other side of the Standard Model, we have the fundamental matter particles. So these particles together make up all of the visible, and I'm emphasizing visible here, all of the visible matter we have in the universe. So there are 2 families. There are the quarks and there are the leptons. So the quarks, oops, that shouldn't be on the screen just yet. The quarks, these form what are called composite particles, meaning they bind together and they make bigger particles, essentially. We mentioned that the proton is made of 2 quarks, 2 up quarks and 1 down quark. You can make all sorts of things with these. There are all sorts of ways you can fit these particular Lego blocks together to make all sorts of exotic things. But really, to make the matter that makes us up, you only need these 2, the up and the down. That's enough to make all of the protons and all of the neutrons. So these ones here are more exotic and lead to more exotic kinds of matter particle that don't live for a very long time. So it's a really tough job for us to detect them and to learn more about them. And then down here we have the leptons. So again, lepton and quarks, just stupid names made up by physicists. And these include the electron, that third matter particle that spins around the nucleus in the atoms that make us up, and its heavier siblings, the muon and the tau. And also it contains an electrically neutral sort of cousin particle we call the neutrino. And each one has their own cousin. Okay? Now these are things we know exist by experiment. We've detected them, we've measured them. But the rather remarkable thing is that we knew most of these should exist before we even detected them. Now that's what I'm talking about when I say there's this rich theory behind the standard model, which is a little much to go into at the moment, but it means that actually most of these particles we kind of expected should be there before we even found them. That's one of the wonderful things about theory and experiment in science coming together. You know your theory is good if it predicts something, and then you see that thing that is predicted. That's a really good mark for your theory. So this is all the matter, all the visible matter we know of in the universe. So are we finished? Well, we've got all the visible matter. We've got 3 forces here that mediate those forces. Don't ask me about the Higgs, that's a whole other conversation. So is that everything? Does it contain all of the interactions and all of the matter in the universe? Well, the answer is no. Not even close. There's a lot missing, and we're going to talk about what's missing later on. So now I want to talk a little bit about quantum mechanics. So quantum mechanics is, as I say, a very bizarre form of science. It changes our notion of what we mean by predictability and what we mean by it changes what we mean by predictability, is I guess what I'll say. But the bizarrest thing about quantum mechanics is that it is science, is that it is real. We don't just have experimental observations that confirm it, we build technologies that rely upon quantum mechanics. You know, the components within your phone rely on quantum mechanics. So it sounds kind of wooey and kind of spooky, but it's real science, and it has real, tangible benefits that we've extracted from it. So before we talk about quantum mechanics and, as a precursor to that, classical mechanics, I want to talk about this word particle that we've kind of been using throughout and using quite liberally, and really sort of break down what this actually means and why talking about particles is actually quite an odd thing to say, right? So according to classical physics, these particles would behave kind of like snooker balls. Okay, they would bounce off one another, they would exert forces by whacking into each other and pulling on each other at a distance, but essentially they would behave like snooker balls or something like that. And a fundamental particle as something that is indivisible, that cannot be broken up into smaller pieces. I mean, think about what that sort of means for a minute. You know, this thing should have no size because it cannot be broken down into smaller pieces, yet it is matter. And in combination, they make different kinds of matter that have size and they have mass. But it in itself is something that has no smaller components, no smaller pieces. Well, then what is it? What is it made of? What would it mean to look at it? You know, talking about these things as solid objects, solid pieces of matter, is a bit of a misunderstanding. They're much more bizarre than that. And when you really pick apart what we're talking about here, you almost have to come to the conclusion that there's got to be something else going on. These things cannot be these indivisible blocks of matter that cannot be broken up. Now, that's not to say that they must be made of smaller pieces, but it's to say they are not so much blocks of matter as something a bit more exotic, which we'll try and get onto later on. So, first of all, to talk a few words on classical physics. So, according to classical physics, the basic prescription is you take some initial information about a state, some initial information about the way the world is. You apply the laws of physics, and then you work out the final state, how the world is sometime later on. With sufficient information about the initial state, sufficient knowledge of the laws of physics, and sufficient computational power, either in your head or using a computer, you can work out exactly what the final state of a system will be. It's deterministic. That's what classical physics says. So, you know, for example, if you throw a ball up in the air, you know the strength of gravity, you apply a couple of equations, and you can work out how high the ball is above the ground sometime later. That's a sort of typical classical physics calculation. Now, if you wanted to break down classical physics into kind of 4 branches, you'd break it up into classical mechanics, which is about moving objects, thermodynamics, which is about engines and heat, electromagnetism, which is about electricity and magnetism, and optics, which is about light and refraction and reflection and how light works. But this information down here, this fact down here, persists through all of these branches of classical physics. And quantum mechanics comes along and it disabuses us of this notion that nature is deterministic in that way. You can know as much as you like about the laws of quantum mechanics, but that doesn't make it predictable. It doesn't make it deterministic. As for, I know where the electron is now, I know the laws of physics, and I know where it is later. It's weirder than that. It behaves in a much stranger way. So the laws of quantum mechanics. Now, I'm skipping a little bit of this because I spoke about quantum mechanics at the museum last year. So one of the links, this is the same QR code I showed earlier, links to the recording of that lecture. So this equation here that comes to us from Erwin Schrödinger is the kind of the first real quantum mechanical law of nature. So it has quite a few interesting parts to it. It has this imaginary number I, the square root of -1, which is a bizarre number that extends the real numbers. And it describes this thing we call the wave function, which we will interpret as a probability. So you can see we're kind of moving on now from talking about finding exactly where a particle is and calculating in a deterministic way what it's going to do, but instead we're calculating probabilities as a description of what the particle is going to do. So the actual, I'm not expecting you to be able to solve this equation in your head. It's a pretty tough equation. It's a kind of equation called a second-order partial differential equation, which you wouldn't solve until you're in your second year of a physics degree. So it's pretty tough stuff. But we're just going to take a look at it because I think it's quite a pretty equation. So what quantum mechanics does is it replaces this fully deterministic picture of initial state, laws of physics, to final state with something more subtle. We have initial state, the sort of more squiggly and foggy laws of quantum mechanics, and instead of coming out with a final state, we end up with a probability of finding the system in a particular state. We can't predict exactly how it will end up or exactly what it will do, but we can give a probability of how likely it is to be doing one thing or the other. So, for example, if you fire an electron at a gap in a wall, the behavior it has is quite different to if you, for example, threw a tennis ball through a hole in a wall. If you threw a tennis ball through a hole in the wall, if it didn't touch the sides, or even if it did touch the sides, you could work out exactly where it would end up because you know how fast it's going, you know how bouncy it is when it hits the wall, and you know how far the wall is from you. So with that information, you can work out exactly where it will end up. But an electron does not behave in such a simple way. The electron, when it's fired towards this slit, it is governed instead by the laws of quantum mechanics, by Schrödinger's equation, and it takes on this kind of wave-like property where it's no longer possible to think of it as a sort of solid block of matter, this rather abstract and bizarre idea of a particle I mentioned earlier, but we think of it instead as a wave. It spreads out and it fills up all of space, and it's not until you try to measure where the electron actually ends up that you can figure out where it's going to be. So if you were doing this with a classical particle, you would fire it at the slit, it would go right through, and it would end up here, and you would know that it was here. You would know for certain if it's a tennis ball. If you did your calculations properly, you'd know where it ends up. But when you apply the laws of quantum mechanics, what you get is not a definitive answer, but you get what we would call a probability distribution, meaning essentially how high these peaks are tells me how likely the electron is to hit that particular part of the screen. Now you notice that although it is most likely to be going straight through the hole and end up on the other side, right opposite where the gap is, there's a non-zero probability that it will end up somewhere slightly to the side. And this distribution will go on forever, meaning there's a vanishingly tiny probability it will be somewhere completely different, very, very far away from the hole where it was fired through. Now that's a fundamentally quantum mechanical process. That's something bizarre, because now I can know as much as you like about the electron, and I can't calculate exactly where it's going to end up in a deterministic way. My answer fundamentally is probabilistic. It ends up over here, it ends up over here. I can't tell until I make a measurement. So there's something weird going on here. This thing we think of as a particle is not quite behaving in the same way as something like a tennis ball or a golf ball. It's not behaving like a solid, singular piece of matter. It's a little bit more sort of spreading out. It's kind of like a sort of puff of smoke. It flies through this hole and it kind of coalesces later on, and then we understand it as a particle. But while it's undergoing this process, it's not behaving as regular matter as we understand it. But you might say, well, surely the electron really has to be somewhere. I mean, I'm saying that there's a kind of probabilistic distribution here of where it may be. Well, yes, but also no. The electron doesn't really decide, in quotations, about where it is until you make a measurement of it. That's the crucial thing. Measurement in quantum mechanics is a key part of determining what's going on. So we go through the slit. The electron takes on this kind of wavy form, and it leaves us with this probability distribution, saying it's most likely to be here, it's possible here, but it's less likely. And actually, where it ends up being overall is only determined when we make a measurement of where it is. Until a measurement is made of that electron, it's not yet determined where it has ended up. Yeah?
How could that be replicated, though, to use if you're never sure where it's...
Like in terms of like technology and things? Well, it's... So, I mean, ultimately, this is how nature works. It does work in this way. So if we want to kind of build things that are working at that microscopic scale, like many transistors that are in our phones and in other pieces of technology they're so small now that quantum mechanics actually has a role in how they operate. We have to understand those laws of nature and try and not work around them, but work with them. So there are various properties in quantum mechanics that make technologies possible that you couldn't do with classical physics. Now, the idea that the electron may be here or may not be here is sort of not one of those ideas that is, well, I'm explaining this badly. That's sort of not the key idea that leads to us making technologies with it. It's sort of, I guess this is one example of that bizarre property that we can then utilize other properties of to build technologies. If that very vague answer makes some sense. Okay. Did anyone else have a question at this point? No? Okay. So we make a measurement, and it's in that process of making a measurement that the electron, it kind of reverts back to being a particle. It reverts back to definitely being something and definitely being somewhere. The way we describe this is that you have collapsed the wave function. You've taken that sort of wavy probabilistic behavior, you've made a measurement, and then your electron has become a particle again, something with a definitive location. So if I wanted to put in kind of a sentence, how I guess I want you to think about quantum mechanics and what it tells us about matter, that is that matter behaves rather like a kind of fuzzy cloud governed by Schrodinger's equation, the laws of quantum mechanics, until it's observed, and then it becomes like a particle again. Okay? Now, of course, that picture seems quite disjointed. We're saying it's one thing, and then we're saying it's another thing. Now, the only real resolution to that is to say, well, actually, it's neither. It's neither a wave, it's not a particle either. It's something far more complicated than both of those things. It's fundamentally a quantum mechanical object that takes on these properties when it's measured and takes on completely different properties when it's not being measured, when it's undergoing a process. Does that make some sense? Yeah? Yeah, Maria?
Well, if you're observing it there and
Yeah.
it suddenly becomes a particle again,
It's okay.
how do you know that it had dissipated into the other potentiality, so to speak?
Well, once you measure it, it takes on this definitive location. So at that moment, it has kind of, you're certain of where it is, so it exists in that state. You'd have to fire it through the gap again to give it that kind of almost potentiality to be somewhere else. So once you measure it, the wave function collapses, and then it becomes something that is in a definitive state. And you then have to make it undergo some process like firing it through the slit again before it takes on that sort of probabilistic behavior again, if that makes some sense. So this seems simple, right? Well, no, it's not remotely simple. So these are two Nobel Prize winning physicists saying it makes absolutely no sense, because it fundamentally does make absolutely no sense. It's completely different to our understanding of how matter and how the world works at our human length scales. But again, I'll say the thing that is perhaps most bizarre about it is that it is true, is that it works. It means we can build technologies from it that rely on us understanding these laws as we have derived them. So it's an odd field of science, but it ultimately is a science. It completely changes the way we think about the world at the subatomic level. It's not like snooker balls bouncing off each other. It's much more complicated. It's a world of uncertainty and probability rather than deterministic physics. So it's a strange thing. Did anyone have any questions at this point? Any others?
I heard it
Yep.
summarised once. It's very much like what you said at the end there.
Yeah.
Matter propagates as waves
Mm.
and interacts as particles.
Yes, yeah. No, that's a good analogy, yeah. Anybody else? Nope. Okie dokie. So now I want to move on to something even more fun, which is quantum fields. So we've spoken a little bit about quantum mechanics. We've spoken a little bit about particles. Now, when you combine two of the great theories of the 20th century, Einstein's theory of special relativity and the theory of quantum mechanics, you arrive at a new theory. It's unavoidable. You have to arrive at this theory. If both of these things are true, you arrive at something called quantum field theory. So after the sort of quantum revolution in the early part of the 20th century, people tried to combine these two fields. And they first of all arrived at a theory called quantum electrodynamics, which is the theory of light and how light interacts with matter. So this is the photon, what I mentioned, is the particle that mediates the electromagnetic force interacting with matter. But as the years went on, we built up other theories that describe all the different interactions, not just the electromagnetic, but the strong and the weak. The one that remains is gravity. That's the one we haven't yet got to. So there are kind of two key equations here that we're combining. One is Einstein's famous E = mc squared from his special theory of relativity. This is the equation that tells us that matter and energy are in some sense interchangeable. You can create a lot of matter you can create a lot of energy by destroying a little bit of matter. You annihilate matter together, matter and antimatter. They collide, they disappear, you release a huge amount of energy. And you can go backwards. You can create matter from energy, from pure energy. So this might sound odd if, in science you've learnt about the conservation of mass. You can't create or destroy mass. And the conservation of energy. You can only transfer energy from one form to another. It doesn't break those things completely, but it basically tells us there's a kind of exchange rate between the two. You can violate energy conservation as long as you violate mass conservation in a kind of equal and opposite way. They can be swapped with one another. This equation here that comes to us from quantum mechanics is one version of Heisenberg's uncertainty principle. So this version of the uncertainty principle, I think, is probably the more interesting one than the position momentum. You may have heard this. You can know how fast something's going, but not where it is. You can know where it is, but not how fast it's going in the quantum world. This version, I think, is more interesting. This is the energy-time uncertainty relation. And what this essentially says is that you can borrow energy from the universe as long as you don't do it for very long. So you can borrow energy, change in E, as long as the change in time for which you borrow that is short enough. So that again seems to violate conservation of energy, which it does a little bit. Quantum mechanics really does kind of change how those things work. But if you combine these two, the fact that energy and matter can be swapped, the fact that energy can be borrowed from the universe, you realize that matter can be borrowed from the universe. You can create matter out of nothing as long as that matter does not exist for very long, which is a bizarre idea. But what it means is that the vacuum of space is not really a vacuum at all. Around us right now, and even in the most empty depths of space, the whole universe is filled with this kind of fizz of matter particles popping in and out of existence and then immediately annihilating and disappearing. That's one of the key ideas in quantum field theory, that the whole universe is filled with this constant fizz bubbling over of particles popping in and out of existence. It's a weird idea and it has some incredible consequences, but again, we kind of know it's true because we've made measurements of these things. One of the predictions of this fizz of particles popping in and out of existence is that if you take two completely uncharged metal plates and you put them near enough to one another, they will experience a force that tries to drag them together. And we've measured that force. So we know that this fizz of particles is there. We've measured it, we've predicted it. And it also has an incredible consequence to how black holes work and how actually black holes do not necessarily live forever. You know, the thing you would have heard about black holes is that they take things in and nothing can escape them once it gets inside. So you would think a black hole should just grow and grow forever because it can only eat and it can never have anything exited. But actually, black holes have a shelf life. They can expire, they can evaporate by this process we call Hawking radiation, and that relies on this fizz of particles popping in and out of existence near the edge of the black hole. And if you want to hear more about black holes, you can come back in 2 weeks where we're going to talk about them for the full time. So this is a kind of nice video here showing this sort of fizz of particles popping in and out of existence. But ultimately, what quantum field theory tells us is that this description of matter as a particle and as a wave, in some sense, is not the complete picture. The most complete picture we have of the way matter works is as what we call a quantum field. So that word makes absolutely no sense when you just say it. But what we imagine is that the entire universe is filled with various so-called fields, meaning, a field is a hard thing to explain. It's this kind of intangible stuff that fills all of space. And a particle is a particular excitation of that field. So, there's an electron field that fills all of space, and an electron is a particular kind of bubbling over of that field, turning into a particle. That's the best description we have of matter at a fundamental level. So it sort of replaces the idea of particles, although we still talk about particles. I call myself, I'm a particle physicist, not a field physicist. But it means that particles ultimately are not the full picture. They are an excitation of this underlying field that fills all of space. Kind of like if you have a pan of boiling water, the particles are a bit like a bubble rising to the surface and bursting out and creating these disruptions on the surface of the water. Okay? So that's a bizarre idea. It's another bizarre idea. So ultimately, we think matter at its most fundamental level, or at least we best describe it as quantum fields, with particles being the excitations of these fields popping in and out of existence. That's what allows for them to appear and then disappear. It confirms all of those properties we measure, all these things we know about the quantum world are reproduced when we describe them as quantum fields. So what is matter? Is it a particle or a field? Well, it's kind of both, sort of. It's really neither. Ultimately, it's this quantum field of which particles are an excitation, a small part of the underlying thing, the underlying field itself. So when we make measurements, we observe particles. Okay, that's what we kind of see. But what goes on in between? I mentioned firing this electron through this gap, and it kind of behaves like a wave, and it interferes, and it has these weird properties where it becomes a little bit nebulous in its existence until we measure it, and then we know it's there. We know it's a particle. Now, this idea stays on when we're looking at quantum field theory. So if you consider two electrons that are kind of moving towards each other, this picture here is a sort of schematic of what we call in particle physics a Feynman diagram. So you're kind of reading time upwards. So here is the initial incoming electron on the left. Here's another initial electron on the right. That's our initial state. And these two are kind of flying towards each other. And forget about what's in here for now. The end result is that they bounce off each other. They end up moving in different directions. And we can measure that. We know the initial state because we can fire them out of an electron gun. And we can measure the final state because we know how fast they're moving afterwards. I've just realized I haven't plugged my laptop in, so I'm not quite sure how much charge it has. Hang on. Oh, my charger's already out. Oop. Just give me 1 second, because if it dies, that'll be quite annoying. Okay. All right, there we go. So we know what's going in, we know what's coming out. But let's focus a little bit now on this fuzzy, indeterminate behavior. This is where the kind of quantum weirdness happens, where we can't really keep track of exactly what is going on inside of this middle bit, where the particles come in and they end up coming out. Now, we know from studying the electromagnetic force that two electrons will repel one another by exchanging a photon. Remember, we said the photon is the exchange particle, the mediating particle of the electromagnetic force. They will fire photons at each other, and that's how they communicate, okay, we have the same charge, we're both negative, so we've got to repel. So is this what goes in the intermediate box? Have we kind of filled in and got rid of the kind of quantum woo, that indeterminate behavior? Well, it turns out no, we haven't quite got rid of it. There's more going on. There's more going on here. So it turns out there are many, many different ways that the electrons can repel one another. That way we mentioned down here is just one way. They could exchange a photon, but also they could exchange a photon in this way from one branch to the next branch. In the middle, they could spontaneously turn into a pair of antimatter particles, an electron and an anti-electron. There are infinite combinations of what they can do, starting off as two electrons coming in and ending up at two electrons going out. And remember, this is still quantum mechanics. This is still ultimately probabilistic. We know that they're going to repel away from each other, but working out, exactly how they repel away, the answer is a probability. It's not a, okay, this one goes at 30 degrees, this one goes at 20 degrees. We get a probability that each one is going to be going a certain way. It's not a definitive deterministic answer. So the way we calculate that probability is done by adding up all of these so-called Feynman diagrams that represent all the different ways the particles can interact. So these are really important tools for particle physicists that represent the different interactions particles can have. They're so important that I have a mark of one on my arm from a misspent undergraduate trip. But they're important. They represent probabilities. And if you want to work out the total probability that these electrons will scatter off each other, you technically have to add up all of these. But the more you add up, the less important they become. As you add more of these squiggles, they become a smaller and smaller contribution. But maybe that's a little technical. So I want to talk a little bit now about the kind of unsolved mysteries, the things about particle physics that we don't know, that we still need a lot of help thinking about. So perhaps the biggest of these is dark matter. So dark matter makes up about 90% of the matter content of the universe, or maybe it's 80%, I should know that off the top of my head. Somewhere between 80 and 90% of the total stuff, the total matter in the universe. Now, that's a pretty bad record for us because it's more than there is of anything else, and we have got no idea about how it works. We don't know what it is, we don't know how it behaves, how it interacts, we just know that it's there. Now, the way we know it's there is quite interesting. So we know that there's all of this matter in the universe that cannot be seen, it doesn't interact with light, it can't be touched, because ultimately touch is due to an electromagnetic repulsion between the atoms in my left hand and the atoms in my right hand. And if it doesn't feel that force, it would just pass straight through my body. So there's dark matter in this room with us right now, streaming through our bodies, but it goes straight through. It doesn't interact at all. Or if it does, it's very, very weak with normal matter. So we know it's there by looking at the spin of the galaxies. There's a kind of little graph here I've put in that shows, first of all, the predicted curve. So if you look at all the stars in the galaxy, you kind of count them up, you work out how dense the stars are in the middle, they're less dense on the outside. You can work out how quick the galaxy should spin and how much that spin should change as you go further from the center. And this is what that theoretical prediction is. But when you actually measure the speeds that these stars are moving at, and you look at different stars that are different distances from the center, and you plot them on a graph, you find the curve is much flatter than it first was predicted to be. So we measure a big theoretical difference in how the galaxy actually spins to how we expect the galaxy to spin based on the number of stars and based on what we know about gravity. So that tells us there's a problem. Now, when you come up with a theoretical versus experimental difference of that size, it usually means you're missing something really big. And in this case, we can resolve that difference by noting that the galaxy must contain a lot more matter than just the stars we can see. It must contain a lot of stuff that is not luminous, not visible. In other words, invisible matter that we call dark matter. That's something that solves the problem. And for a long time, that was maybe a bit of an odd suggestion. You might just think perhaps we're using the wrong equation. Perhaps we just don't understand the laws of gravity instead. But we've since made other measurements that I'll touch on later that tell us dark matter really is a particle. It really is. There is matter in the galaxy that we cannot see. It's not just a fact of our misunderstanding the law of gravity. There's something going on there where there's matter present that we cannot see. But we don't know what it is. We don't know whether it's not made of quarks or what kind of particles are part of it. If you think about the mantra of a particle physicist, we want to break up matter and understand what it is at its most basic constituent pieces. We haven't yet done that with dark matter. So it's an enormous open problem. It's an enormous failing on our part that we don't yet know what it is. But it's something that I think could be solved within the next few decades. So if you are a young scientist now, it could be an exciting time. You might be one of the people working on this when they discover what it is, either detecting it experimentally or coming up with the right theory that means we know where to look for it. We know what kind of sort of particle it might be before we try and detect it. So this is a big problem. We don't know what dark matter is. So it doesn't fit anywhere on the standard model, as I say. It's not in this list of particles and their interactions that we have so far. It's something different. We don't know whether it's made of lots of smaller pieces, whether there are lots of different types of dark matter. It's not necessarily just one particle. There could be an entire dark sector, as it's called, lots of different dark matter particles, but it's completely mysterious. Now, we're trying very hard to find it. There are lots of experiments trying to detect it directly by actually measuring the particle, or trying to detect it indirectly by looking for the things it might decay into or turn into. And indeed, there are also attempts to try and measure it using astrophysical or cosmological data. So this cluster up here, the bullet cluster, is one of the pieces of evidence that really changed a lot of minds to realize that dark matter is a kind of matter. It is a sort of particle, not just a gap in our understanding about the laws of gravity. Now, this bullet cluster, I believe, is formed from two colliding clusters. And there are kind of two regions here. There's the pink region, which is luminous matter that you can actually measure. You can see that stuff there. It's dust, it's gas. And then there is this shaded in purple. This is a sort of false colorization. But shaded in purple is matter that we know is there because we can tell the influence of the stars behind it, that we know there's stuff there, but it's much more spread out than this matter in the middle. Now, the reason for that is that this stuff here that we know now to be dark matter, because it doesn't interact with any other matter, it can just pass through things, it's not affected by friction or drag as these two clusters have collided. So the regular matter in pink has been slowed down by friction, because as these these gases and dusts in this cluster have come together, they've slowed down as they have friction, as they rub past each other. But the dark matter has just carried on flying through because it doesn't feel that friction. It doesn't feel a kind of contact force with the other matter. So this cluster here really changed our understanding of dark matter and confirmed that it has got to be stuff rather than just a misunderstanding of the laws of nature. So this experiment here, the xenon experiment, I'm not going to pretend I know much about these experiments because I'm a theorist, not an experimentalist. But essentially, we're hoping that a dark matter particle will come through. It will scatter off one of these xenon ions in these enormous tanks of liquid, and it will create a signal that we can detect as a form of detection. So there are lots of experiments set up around the world where we're trying to find dark matter and trying to find out more about it. But so far, none of them have found anything that fits the profile of what we think dark matter should be. So it's still a very open problem. Does anyone have any questions about dark matter or anything as we're going through? Yeah, Matt?
If dark matter
Yeah.
Why would we be able to detect it?
So I should say it interacts gravitationally in that it has a weight. So that's how it affects the way the galaxies spin. Now, we know that it doesn't interact with light, so we know it doesn't interact via the electromagnetic force. We don't think it interacts via the strong force, but even so, that force is kind of not very long range, so we wouldn't be able to see it with that anyway. But we kind of hope that it interacts via the weak nuclear force. So there are various models of dark matter. So one I like the name of is called a WIMP, which is that dark matter is a weakly interacting massive particle. So there are lots of models where it would interact via that weak force. But ultimately, I don't think there's any reason it has to interact via the weak force. It could just interact purely via gravity, which means all of these experiments where we're trying to get it to knock into another particle and produce a reaction would be a complete waste of time because it just wouldn't. But we know that it does interact via gravity, so it has some signal that it's there, but it then becomes a lot harder to think about how you use the gravitational effect it has to work out something about the particle nature of it. That's almost impossible. Does that make some sense? Yeah. Any other questions? No? Okay. So the other unsolved problem we have, which is arguably an even bigger problem, is this problem of the quantum theory of gravity. So we mentioned that these four particles here provide the forces of the strong force, the electromagnetic, and the weak force. But they don't provide the gravitational force. We don't have a way of understanding gravity in this context, in this way of particles exchanging to communicate forces between matter. We understand gravity in a very, very different way, which I'm going to talk about in the next lecture in 2 weeks' time. So Einstein tells us gravity essentially is curvature of space-time. But that's a theory that works for very large things. It works for things like planets and stars and galaxies, but it doesn't really work for microscopic things, for subatomic particles. So there's a big gap there in our understanding. Gravity and Einstein's theory of it works for very heavy things. Quantum mechanics works for very tiny things. So when you start crossing that gap where you're in the middle, as you do when you're looking at the singularity at the center of a black hole, you need a different theory, a theory of quantum gravity. So these two theories, quantum mechanics and general relativity, Einstein's theory of gravity, are the kind of two pillars on which modern physics is built. They're how we understand things from the subatomic scale to the very largest scales in the universe. But when we try to bring them together and explain gravity using particle physics, they don't work. There's a contradiction there. It leads to all sorts of crazy results, like we mentioned that in quantum mechanics, the answers you get are probabilities. You find a probability that something will happen a certain way. Well, when you try to do this for gravity, you end up with things like probabilities that are greater than 1. And of course, if you know anything about maths, you know you can't have a probability greater than 1. That's a failure in our calculation. So something is going wrong there. So understanding quantum gravity is one of the main challenges of modern theoretical physics. And if we could do that, we would unlock a lot of information about what's going on inside a black hole, and also about what was going on in the very, very early universe, when our universe, being born from a Big Bang, essentially was a singularity. All the matter and energy in the universe kind of squashed into a single point, so both very tiny and very heavy. Quantum gravity could teach us more about what's going on there. And that's actually all I had. So does anyone have any questions? And this is also the 1 hour mark, so if you're desperate to leave, which again I wouldn't hold against you, you feel free to leave. But if not, are there any questions? Yeah.
I was just wondering about the early investigations when you put up some of the slides. It was saying that things were discovered in the 1920s.
Yeah.
And some of the theories were laid down then.
Yeah.
I just think this is marvellous. It's so long ago. I mean, that they didn't have sort of computing power there. I mean, how do they work out these things?
Yeah, I mean...
I know it's quite a nebulous sort of...
No, it's a good question. So, yeah, in the 1920s, that's okay. The sort of early 1900s to 1920s is when we really started to learn more about quantum mechanics as a whole. And it comes from an observation that doesn't conform to what we know about physics or what we thought we knew about physics at that time. So there's this paradigm-shifting moment in the early 20th century called the ultraviolet catastrophe. So physicists being very dramatic in that name. But essentially, when we tried to do a calculation to predict, how much energy is emitted by a hot piece of coal. A hot piece of coal is hot, it glows, it releases heat, it releases light. When we tried to do that calculation using classical physics, the energy that comes off is sort of infinite. It's a billions of times larger than what you actually get from a hot piece of coal. So there's a huge gap there in the theory and what we actually observe, what we measure experimentally. Now, the early origins of quantum mechanics are quite odd. So the word theory in science is sometimes thrown around as, oh, I have a theory, and it's, if you're just talking to a bloke in the pub who's got a theory about something, that usually is quite unfounded. But in science, a theory has a more serious meaning. It means there has to be some kind of motivation, there has to be some kind of evidence for what your theory says. You can't just make stuff up. But the origins of quantum mechanics really test that idea of not just making stuff up to breaking point. What essentially happened is the early kind of quantum pioneers had a bit of a guess about, well, let's see if we do this to the equation, does it make the calculation work? Well, yes, it does. We can now calculate how much heat comes off a piece of coal. Now we have to look at that equation again and think, well, what does our guess actually mean? Oh, it means that the energy that's being carried away by light is quantized, meaning light is not a wave, it's behaving as a particle, as a piece of light. And that's a rather remarkable thing that goes against all the conventional wisdom to that date of what light is. So it's almost a reverse thing. We have an experimental problem we can't explain. We then add a theoretical, basically, shot in the dark to that, and then we interpret that shot in the dark as being light is made of particles. And it's from that that we then come to re-examine all the other kind of matter in the world, the protons, the neutrons, the electrons, which we think of as solid pieces of stuff, and we re-investigate and we look at them and we see that actually they have properties that are rather more wave-like. So matter is not just solid pieces of stuff, it also behaves like a wave. So it comes from that initial discrepancy between theory and experiment. And yeah, that happens in the early 1900s, which is quite remarkable because, you think there's no calculators, there's no computers of a conventional sense, so all of it's done by hand. And oh yeah, well, it still is a chalkboard. That's still where I do most of my work, but at least I can then use a computer after. That's a really good question. Any other questions?
What skills do you need to be a particle physicist? What sort of people and what sort of skills would do well in this field of science?
Yeah, I mean, there's no miracle talent for it. It's not a, you're welcome. It's something anyone can do, right? I mean, it's something that takes a lot of work. It takes a lot of curiosity and imagination, but it's not something that only some people can do and no one else can do it. Anyone can do it if you work hard enough at it. If you work hard at doing the maths, you've got to be really good at maths as well as good at science. But I believe that's something anyone can do. It's not just some people are good at maths and some people aren't. Anyone can learn it. I mean, I'm perhaps not instinctively that good at it naturally. I didn't do that well at it in school until later on in my schooling career. But by working hard at it, you get better and you improve. So I would say curiosity. Curiosity in all of the sciences is the most important thing. Whatever kind of science you're doing, it's all about curiosity. Yeah?
How do we know that the observable universe exists?
How do we know the observable universe exists? Well, what do you mean? Sorry, say again.
How do we know all the placements of the galaxies?
Well, by observing them, right? We've developed telescopes and things. We can observe where the galaxies are. We know knowing how far away they are is an interesting question because obviously you can't just kind of eyeball it and say, okay, I think that's about 1,000 light years away. There are techniques we have for measuring distance. So some of them involve a special kind of supernova that's more properly called a nova or a type 1a supernova. And these are quite interesting. And what's interesting about them is that they always flash with the same brightness. Wherever they happen, they always have the same brightness. So if you know that special kind of supernova is happening and you see it happen in a galaxy, you can measure how bright it looks to us on the Earth and compare that with how bright you know it would be if you were stood right next to it. And from that, you can work out how far away it is. So we've got all these kind of tricks of how we know certain processes work in the universe, by comparing how they look to us on the Earth and how we know they would look if you were sat, right next to them, we can work out distances. But there are other methods too. All of them are really interesting and really kind of ingenious, but that's one of the ways we know how far away different galaxies and different stars are. It's a really good question. Any other questions? Yeah, Peter?
One of the things that I don't think we know is how to calculate the masses of the particles. Do you think we'll ever be able to do that in your lifetime?
Yeah, I don't know. I mean, this is one of the really interesting things that string theory does. It can calculate masses of particles. It doesn't calculate masses of particles that are the particles we have in our universe. So it's a kind of model of how you could have an overall theory, a sort of theory of everything, a theory of quantum gravity that predicts how heavy all the different matter particles are without putting any other information into them, which is quite remarkable. Whether we actually reach that something manageable that works for our universe, I don't know. It's one of those things, I mean, maybe we dig all the way down and we find this theory of everything that makes everything fall out nicely. The mass of a proton comes out, the mass of the electron comes out, all the different coupling strengths of the different forces fall out. Or maybe it's just like some onion where we keep peeling away layers and we get a little more information, but ultimately you never get the final picture that puts everything into perspective. So I don't even know whether we will ever arrive at that theory. That's certainly what the hardcore theorists, the string theorists, hope we will. That's their goal. But I don't know. It'll be nice, It'll be interesting. It's a good question. Any other questions? Yeah?
What are some of your own theories?
Some of what?
What are some of your own theories?
Some of my own theories. Well, some of the things I've worked on. So dark matter is one thing I work on. So in particular, we are trying to figure out whether dark matter could be detected by looking at the signatures it would leave in the neutrinos. So these are these kind of nearly massless, zero charge, very hard to detect particles, by looking at the traces it leaves on those neutrinos that reach the Earth from supernovae. So if you go back through the whole kind of history of the universe, there's billions and billions of supernovae have happened throughout the universe's history. And when those supernovae happen, they release huge amounts of these particles called neutrinos. And we kind of have a hunch that if dark matter can interact with neutrinos, it would sort of sap away a bit of that energy that the neutrinos have when they reach the Earth. So by investigating the energies of these neutrinos that come from all these supernovae in the universe's history, if we find a dip or a sort of verge taken out of it, that would be an indication that something is there that is sapping their energy that is not observed by us. It's not visible matter we see in the sky. And that would be good evidence for dark matter. The difficulty is neutrinos are almost as hard to detect as dark matter because they also don't interact with light. So there's trillions of them passing through this room right now. But they do interact via the weak force, meaning you can occasionally get them to bounce into something and create a signature that we can detect. So they're not quite as bad as dark matter, but still pretty bad. It's like we're trying to measure dark matter by measuring something that's only slightly easier to detect than dark matter. And if we do that, if we find dark matter from that, I'll go off and I'll collect my Nobel Prize. But really, when you're doing dark matter research, you're not actually hoping to find dark matter. You're just trying to rule out, okay, we know it's not that, we'll try again, another thing. It's really a question of, okay, it's not that, it's not that. That's the sort of extent of dark matter model building, unfortunately. It's a really good question, though. Ooh. Yeah, young man.
You told me about the E equals mc squared or something similar.
Yeah.
What would the E stand for and what does the M stand for?
So the E is energy, the M is mass. So it's the exchange between energy and mass. You can destroy mass, create energy. You can use energy to create mass. Yeah. Any other questions? While you're having a think, I'll just put up here. So every other Sunday in the foyer of the gallery, I do a science drop-in, which is really nice. People come along every week. We have a chat about science. I share things I've learned. People share things they've learned. It's a lot of fun. And these are roughly every fortnight in the foyer of the Beecroft Gallery. So there are the kind of upcoming dates. You could look, if you like, on the webpage where I post summaries of what we've spoken about, and I also post when the next one is, for example. So the next one is next Sunday. You don't have to stay for a full hour. You can just pop along, ask me something, then pop off and do your shopping, whatever it is. But yeah, that's one thing I wanted to flag. Another thing is that these lecture slides, this is another link, are posted here if you wanted to review any of these lecture slides and ask me more questions about them. So please do take a look there if you like. These are both linked, by the way, on the same QR code I showed you earlier. So those are linked on that Google Doc I showed you. And there are other lectures coming up. So in 2 weeks' time, we're doing a lecture on black holes. 2 weeks after that, we're going to talk about science fiction. So we're going to look at some of the much more kind of speculative ideas in physics and how these apply to what science fiction writers have been putting in their materials. And then lastly, we're going to talk about some of the most bizarre ideas in theoretical physics. So this is almost stretching the definition of science because these are very much theories that are untested and in some cases cannot be tested. So we'd be talking about things like extra dimensions and wormholes and bizarre structures and things that we don't know exist but are still main topics of discussion in theoretical physics seminars across the world. So that's something I hope to introduce you to then. But that's it. Are there any last questions? If anyone wants to ask a question at the end, I can stick around. You can come up on your own if you like. Yeah, Peter?
Question about a question.
Okay.
You asked a question at the start where I think I was in a minority, where most people said, yeah, there's something else
Oh, right.
further down,
Yeah.
maybe not.
Yeah.
What do you think are the clues one way or the other? What sort of things hint that there may be another layer, or what sort of things hint that maybe there isn't?
I think ultimately it's stuff just we can't investigate yet. It's something where if there was a clue one way or the other, we'd have a kind of we'd have an idea of how likely it is one way or the other. But we can't really probe these things. You know, experiments that probe sizes smaller than quarks just don't really exist. If they did, you know, it would be a way also for us to test the quantum behavior of gravity. But these experiments are too high energy. You need a particle collider, you know, the size of the moon or something. So it's just not something we can build, not something we can do. So I'm kind of agnostic on that front. I tend to believe there should be a fundamental particle, something that is indivisible, but I don't know whether the quark is, you know, the quark is an example of that. It might not be completely indivisible. Okay. That's okay. Well, I'm going to let you all go. And if anyone wants to ask me anything else, you can come up to the front and ask me. Okay? Thank you very much. Thank you.